Hey, hi there. So, welcome to this session on SystemVerilog Cover Group for the functional coverage. So far as a part of this training, we have been looking at the coverage-driven constraint random verification, right? So, using this approach is what we have been discussing, and we have looked at constraints, for example, and we have understood that when you randomize something, right, you need metrics to see whether the stimulus that we have generated has completely exercised the design. So we need and we have looked at how coverage can serve as one of the key metric as a part of the coverage metric overview, and there we had looked at two types of coverage metrics. One is the code coverage and another is the functional coverage. And when we had contrasted, the main difference was the code coverage was looking at the implementation, whereas the functional coverage was looking at the requirement specifications. And in terms of the key technical difference, the functional coverage was able to address the dimension of time. By that, what do I mean is that if something is, if the two things are happening concurrently, that's something the code coverage will not be able to tell you directly, or if there is some temporal sequence that is taking place, that is something the code coverage will not be able to tell. So those are some of the challenges with the code coverage, and that's where you need the functional coverage. There are two ways to implement the functional coverage. The one is, as we have seen, we can use the cover directive with the assertions for the low level interface signals related functional coverage. And in this session, what we are going to do is we are going to look at a cover group construct, right, and how to use the cover group construct for implementing the functional coverage. Here is the agenda for this session. So first we will look at how to implement functional coverage. What do I mean by this is that if there were no cover group construct available, then how would we have implemented the notion of functional coverage? We will briefly look into it to understand what capabilities does the cover group construct provide us, and then we'll quickly look at cover group use cases. Here we will just quickly refresh the cover group. We will contrast it with the assertion based coverage quickly to sort of make the distinction as to where exactly the cover group construct will be useful, and then we'll go to the elements of cover group. So any coverage is essentially finding out how a particular variable is taking a different values, right? That's the fundamental thing. Now when it has to check a particular variable, then it needs to have the ability to access that particular variable, right? So cover group construct can access those variables that it needs to cover through two ways. One is when you put it in a container like a module, class, interface, or a program block, whatever the variables or the properties that we have defined within that particular scope, the cover group construct can access those variables. For example, a task or a function that we have defined in the class can access the properties directly, right? The similar way, even the cover group construct can access the variables that are defined within the container. That's one way. And second way is like a class wherein we pass the arguments through the constructor. We can pass the arguments to the cover group as well. So we will look at it, and then what are the ways in which cover group provides us a way to sample the information. How do we control when the cover group should sample? So we look at ways for doing that. And cover point is essentially a way to cover a particular expression or a variable, right? A single expression or a variable, you cover it through the cover point. And when you have multiple expressions or multiple variables and you want to cover the combination of values that can be taken by that group, then you use the cross. Okay, and then we'll come across this term called bins. Bins are specifically like a named values, wherein you say that, like, when you cover a particular variable, then it is going to take different values. So you can give a name to a particular value, or to a group of value, to a transition, right? So how do you define them, and how do you manage them. We will cover them in the context of both the cover point as well as cross, right? So for both of them, you can define these various named value pairs in a way, right? So how do we define them and how do we manage them? We'll look at it, and then we'll end this session with the list of coverage options. So coverage options essentially help us control the behavior of a cover group, and then that control of the behavior manifests itself in the form of the way the results get reported. It changes based on how we set the options. So we will look at those different options and how do they change the coverage that gets reported. So before we jump into the details of the cover group construct itself, let's understand that if there were no cover group construct, how would we have gone ahead and implemented the functional coverage? Okay, so in order to do that, let's take a very simple problem. So let's say we have a simple memory type of an interface. We can take a simple SRAM type of a memory interface. So to a memory, what we can do a read write access to memory at different addresses, right? That's a simple thing we can do. So I am considering very few parameters over here. Of course, we can expand the scope to many more things. Just to make the point, I'm considering few variables. So for this type of a memory, what would be the key stimulus? We would be generating the access types and address. Of course, we will be randomizing the data as well for the in the case of write, right? And what do we want to see as a part of our functional coverage specification? We want to first see that we are able to issue both the type of accesses, that we are able to issue read and write. That's what I would like to see. Second, I want to make sure that all important address or address ranges must be covered. If it's a small address range, then we can maybe cover each and every address, make sure that it has happened. If it's a large address range, and then we at least we divide it up into few ranges and make sure that the beginning range somewhere in the middle as well as towards the end, right? So all the ranges are covered, and then what we need to make sure is that if we are dividing them up in the ranges, then to each of the range, right, we need to make sure both the read and write, both of them have taken place, and then we would like to see a good mix of read and writes, right? So what do I mean by that is I should be able to see, like for example, I had back-to-back reads. So I had back-to-back reads and then I had back-to-back writes, whether it works properly or not when I do back-to-back accesses. And then if I have a mix, that is I do a read and followed by that immediately I do a write, how does this behave? And then I do a write and then followed by that immediately I do a read, how does it behave? So this way I want to see the transitions to ensure that I have had a good mix of it, and I am ignoring data for the moment. Well, let's not increase the complexity at this point. And then for each one of them, we are interested to look at that we have had a good number of hit counts. It should not happen that, oh, I have just done some 4 reads and 4 writes and we are saying, okay, you know, things are all working fine and we are able to see all of these criteria as being met. We need to have some good hit counts, that at least we have done 100 reads and 100 writes minimum, right? I'm just talking about for a simple memory. At least we have had done like a 3-digit type of accounts for each of the access types. So this is what I would like to see as a part of the functional coverage. Now, if this I want to see, right, then how do I go ahead and implement it? Now we have already done enough of Verilog and SystemVerilog that we can design our own system to implement this coverage. Can we not? Because each of these items that we are talking about is nothing but a simple counter. Okay, like for example, I can just implement one simple counter that increments whenever the read takes place, whenever the write takes place, right? So using that, I don't worry about initially about the addresses. Of course, I can track it in different ways, aggregate and generate it, but let's say for the simplicity, I just keep 2 counters, one counter when I increment when the read takes place and one counter when it takes place write, irrespective of the address. That is one pair of counters I am maintaining, and then a simple counter to increment access to either the specific set of addresses if they are fewer, or to, let's say, 4 ranges of addresses, right? Like let's say I have 4 range, and then whenever the access takes place to each of the range, I will increment. I'll keep one counter and I will increment that particular counter. Can we not do that? We take the address range and we say if the address falls within that range, if it is greater than start and less than end, I will increment that particular address range counter, right? So that is the way I can figure out that whether the addresses are getting covered, right? So I'm keeping that count for that. And then what I will do, I will combine the like the access type with the address range type to make sure that each of the address, a specific set of addresses, if they are fewer number, and or the address ranges have been accessed in both the forms. That is, I have done the read access as well as write access sufficient number of times to each of the ranges, right? So I want to ensure that, because I don't want that all my accesses are just accessing the beginning beginning part of the beginning quadrant of the address range. If I divided it in 4 and it was only accessing the first quarter, and the remaining 3/4 of the quarter have very few accesses, we do not want that. We want a good spread. So we want to ensure that we will look at the count and ensure that it is a good spread. So we will keep a count per range, how many reads and writes are taking place. Now, of course, one thought might come in your mind that I can use this information to derive this first and second. That's possible, but let's say for the simplicity we keep everything separate. And then what we do, we can keep a queue, 2 deep queue, and every time I give an access, I just push it in, and then when it moves out, when I have 2 accesses, I pop the first one and keep moving the next one. So series of them keep moving. At any given point of time, we have a window of 2 transactions, and looking at the window of those 2 transactions, now I can figure out the transitions, right? Like for example, read followed by read, or read followed by write, write followed by write, write followed by read. Those transitions, I can keep track of them, and I can implement a count, right? And like for maintaining all these counts, what's the data type that we will use? Of course, we will use the associative array, because it's a sparse type of a data. So we can use a associative array, and in the associative array, we will keep track of all these counts. And what we will do at the end of simulation, we will use the final block. In that final block, we'll dump out all these counts in the simulation log file. Okay. Now, when we dump that out, I will be able to come to know that in a given simulation for a particular test, what are these counts, right? I will come to know how many reads have happened, how many writes have happened, and for each of the address ranges, how many total accesses have taken place, and then for each of the ranges, how many reads have taken place, how many writes have taken place. I will have that breakup, and I will also have the breakup of counts, right? Transition counts, how many times I have done read followed by read, how many times I have done write followed by write, and how many times I have done read followed by write, and vice versa, right? For each of them, I will know the count for a particular test. Now what I will do, we can write one more script which takes in all the data from these multiple tests that I have run, aggregate them together, right? So I can do that, right? Like I can take the total count in this particular test, the total count in this particular test, total count in this particular, aggregate them and average them out, and figure out that like what's the coverage that I'm hitting. Okay, let's say in one particular test I might be accessing the first first quarter of the region much more, and in the another test I am accessing the last quarter of the address range much more with the higher counts. But when I put them all together, I am able to see a nice distribution, then that is fine. So across regression, then I can say I have a decent amount of coverage. And one test might be doing only writes, and one test might be doing read only, and those tests might be contributing to like write followed by write and read followed by read transition counts, and a mixed test might be contributing to read followed by write and write followed by read. All that will combine when I aggregate the counts from the different test simulation log files, right? And then I'll report a final number saying that what has been covered and what has not been covered. And you might discover that, oh, the third quarter in all the 4 whatever the regions that we had defined, it's not covered, or that particular region has not seen a write or something like that. We will be able to uncover, and then we'll probably change the seeds or probably tune our constraints distribution to make sure that it targets that particular region. So this is how we can build a basic functional coverage model. Okay, and this type of an understanding is important to get the primary concept that all that we are doing is whenever we are given a particular variable, okay, we are just counting the number of occurrences of different values for that particular variable. This is all that we are really doing. Okay, and you will be able to see that each of these first two items will become cover points, and the second one, that is not only that we are independently covering the access type, independently covering the address variable, then we are combining them to make sure that all the four regions have seen both the read and writes as well. So first of all, we are checking whether read and writes have happened. Then we are checking whether all four regions have been accessed. Then we are combining both of them and saying, okay, all four regions have been accessed in both read and write, that all the combinations we are covering, and that is nothing but your cross. Okay, so this is the basic idea behind the the cover group construct, and in the next few slides we will really see that if we solve the same problem using the cover group construct, how will it look like, and when we define it, you need to keep this background in your mind, because this is what is really happening under the hood. Now you don't really need to actually create associative array and keep track of how many counts are taking place based on the transactions coming in from the monitor, right? The cover group, once you implement a cover group construct and once you compile it, the simulator will set up the counters for you to track this particular information and eventually put that in a database, and then it will provide ability to merge the databases and provide you the final coverage result, right? So those aspects will be automatically taken care by the simulator, but under the hood it's nothing but tracking the counts of the different values being generated. So let's look at which are the areas where you use the cover group construct and which are the areas that you generally use the property based functional coverage. So this any rand variable that you have in your test bench and the design registers, because design registers typically get modeled using the RAL in UVM, so even those are covered using the functional coverage, right? So typically are covered using the functional coverage for different combinations and transitions. So they are all, any of your test bench rand variable and the DUT registers, they are generally covered using the cover group construct. And the some of the popular use cases are like you have your monitor will generate various transactions, and all the functional coverage based on those transactions is all done with the help of the cover group. Okay, and there could be multiple interfaces, and each of those interfaces might be having monitors. So you take information from all those monitors, and sometimes you take information even some of the DUT state and test bench state, and implement complex scenario, and then scenario coverage, and then you can implement whether all the interfaces, multiple interfaces where they are active at the same time, and you can also implement like lot of if you have any like a state machines that are implemented at the test bench level, those state transitions also can be covered using the cover group. And then the test bench components maintains various state information, like for example I might have a multi-port design, how many ports were connected, whether it's only like have we done traffic with only one port, two port, three port, four port, and on each of the ports has it gone through different state transitions, and all that you can do it using the, I mean it's generally done through the cover group construct. And then even in the FIFO test bench we have seen a configuration object. The configuration object, we have seen two types of configurations, a structural configuration as well as the functional configuration. So both of them I think can be covered using the cover group construct, because anything that is generally modeled in a class based word, right, is covered through the this is the general rule of thumb, right? Anything that is modeled in the class based word, you cover it through the cover group construct, and anything that's sort of modeled in the signal level word or the module type of a word, you rely on the property based coverage. Okay, and even the stimulus that gets generated at the top, eventually in the UVM we will see that UVM sequence we are going to use all the stimulus that is generated. We can use the cover group construct to cover whether we have generated and exercised the various sequences of stimulus. right? And then some of the RTL information also can be covered. Some microarchitecture based functional coverage can also be implemented. Okay, see, predominantly, primarily, you tend to use the assertion based coverage for the microarchitecture, but that doesn't mean you cannot do the the functional coverage for the microarchitectural aspects as well. It depends on what exactly you are covering, because even the cover group construct provides the ability to sample information at every clock. So you can potentially, and some of the transition coverage constructs have the equivalent capabilities, not exactly, but sort of similar type of capabilities as what we have in the sequence, the property sequence operators. So you can potentially cover, but when you look at it as a primary focus area, anything related to design and signal levels, it's a property based coverage. Anything that is class and the rand variables is the cover group type of a coverage. And what cover group requires ultimately is what it needs to cover and then when it needs to sample. So once you have these two information, then you can apply the cover group construct. Okay, so that is the bottom line. So even in the design, you can figure out which signal I am going to cover. I am going to cover address, and when am I going to sample? I am going to sample on every clock when some valid signal is asserted, right? So that way you can apply it to any either the design as well as the test bench. Okay, so in the previous slide, we looked at that the cover group is very well suited for any class-based coverage implementation or the class-based variables primarily, but secondary, it can be used for the microarchitecture or the interface signal-based coverage as well. But primary for the microarchitecture and the interface signal is the cover property based functional coverage. So anywhere you have a temporal sequence of events and the relationship between the events that needs to be covered, then the property based coverage is a better fit. Like for example, any handshake sequence between your control signals on a bus protocol, or any power state transitions that appears as a state machine within your design, and in terms of microarchitecture, if the two blocks are interacting with each other and there is some sort of a internal handshake sequence, those you can cover. And if you have a pipeline within the design, many times to improve the performance, the designs have pipeline, and you want to check whether all the pipelines have are seeing the combinations of different operations taking place, right? So for those type of things, you can use the property based coverage, but please take a note that some of them you can also do it with the cover group. It's not that you must do it with the cover property, but it's more suitable. That's the point I'm trying to make. And then so typically any interface signaling protocol microarchitecture, these you cover using the properties, the low level things, and the high level protocol aspects are covered using the cover group. And like when the sampling is clock and then there is a timing relationship information, that is what exactly that you're trying to cover, that you have asserted a request and how many how many different number of clocks it has taken for the grant to come. So some things like that if you want to cover, then the assertion, the sequence based coverage provides lot many more flexible constructs. So you can use cover directive with the sequence as well as with the property to implement functional coverage using property for the lower layer coverage. Okay, so now we will look into the details of the cover group construct. So cover group is actually, it behaves like a user defined data type, very similar to class. Okay, so what do I mean by that is that you create a cover group a declaration, and within the cover group declaration, as we have seen, the different components will be there. You have cover points, you have crosses, you have options and everything. So once you have created a cover group declaration, then you can create multiple instances, and to create the multiple instances you use the new, and then any arguments that we have defined as a part of cover group declaration, that you pass it using the new. So in that way cover group construct behaves similar to your class data type. That is, you create a declaration, and once you have created a declaration, just creating the declaration is not enough, right? For example, for property, just declaring property is not enough. It has to be combined with a directive, right? So similar, and just declaring a class doesn't initiate its participation in the simulation. It has to be you have to declare a handle and construct a object by calling new. Similar to that, in the case of cover group, you create the declaration with the cover group name, and then define your cover points and define your classes and end group, and then you need to create an you declare a sort of similar to the class, you declare a handle, and then to the handle, when you say new, is when really that particular cover group becomes active and enabled to gather the functional coverage. If you just declare it, nothing happens. Very similar to property, right? Unless you combine it with directive, nothing happens. So same way, you have to declare it, and then you have to declare a handle of that particular cover group, and then you have to say new. Okay, so there is one special case that if you declare a cover group within the class, so as we have talked, class and cover group are sort of like, there is a good integration between them. That's why for anything class based property coverage, cover group is the best candidate, because anyway you cannot put the temporal assertions within the class, right? So cover group is always the preferred choice. And so the integration or the facilitation that we have when you declare the cover group in a class is, so they are, first of all, there is a term for that. So when you declare the cover group within the class, what do I mean by that is, you have some class, and within that you say cover group and name of the cover group and end cover group, the declaration that you are providing within the class body, then it's called as an embedded cover group. Okay, and what happens is, for the embedded cover group, there is an implicit instance, okay, that gets declared with the same name as cover group. Okay, so if you have declared a particular cover group, then within that, like for example, you don't need to declare the handle for the cover group, the name of the cover group and the handle. Like let's say I have declared a reg cg as a name of the cover group, then reg cg space reg cg. Okay, like that, one handle will be created automatically, and you just need to new that particular handle. So when we go further, when you see the examples, this point will become clear. However, you can instance more cover groups, and then you can declare more handles of that particular cover group, because it only declares one, right? So you can declare more of them, and you can new them and use it. So that is not a problem, but by default it already creates one cover group handle for you, which you can utilize. And then any of the cover group that you declare within the class can access both its local and protected properties as well. But with respect to inheritance, right, like the cover group doesn't really participate in the object orientation. What do I mean by that is that you declare a particular cover group within a particular class, and then when you extend the class, right, you can't modify any characteristics of the cover group that you have defined within the base class, right? You can't go ahead and add a new cover point to it or new cross to it. But what you can do is you can modify a few options, but beyond that you can't change anything from the inherited derived or a subclass, right? For example, for constraints, we could override a constraint from the subclass, right? So some things like that you can't do with respect to cover group. Only you can change options, but you can't modify any other aspects of the cover group that you have defined within the base class. So we can, in that way, we can say that the cover groups are not like they do not provide any object oriented type of capabilities, but still they have these embedded cover groups have this additional advantage that they provide you one built-in handle, and we'll look at that in the upcoming example. What does it mean to learn a cover group? Okay, so what are the aspects that we need to learn to say that we have completed understanding a cover group construct is? So a cover group construct is first made up of cover point. So cover point, you think of it like it's a representation that's going to cover one particular variable. Okay, so cover point will cover one variable or one expression. Okay, so what are the different values that are seen on one variable or one expression? Cover point is responsible for that. Okay, and then each of the cover point now needs to have the ability to capture various values that are seen on that particular variable or expression. Now, how does it do that? It does it with the help of legal bins, which are the legal values that a particular variable or expression can take. Then the illegal bins, which you do not expect a particular value to be seen on a specific variable, or ignore bins, which you don't care, you are seeing some values but you don't intend to really worry about it, or it's not important, then you can ignore those values. And then how do you kind of generate automatically the different so if I have a like a 32-bit variable, then how do I group them into different values automatically, right? So because if I allocate one bin which is a name for a particular value, like in a enum we give a named constant, right? Like similarly bin is a name for a set of values. So if I give one bin per value, then it will become so like a 2 raised to 32 will be like a 4 gig type of a value. So how do you automatically group them? So that is there. And then wildcard bins will help you define the bins in a much more compact way when you have few bits of a vector that you don't care. We'll look into the details of each one of them, but I'm just giving you a lay of land over here in terms of the cover group construct. And then when you need to cover the combinations of multiple expressions or multiple variables, right? So as we saw in the previous example, that independently we are able to do read write coverage, independently we are able to do the address coverage, but to ensure that for all the regions of the address variable, are we doing the read write or not, right? So that is where the cross comes into play. And even for the cross, now what you have is, instead of one expression or one variable, you have multiple of them. So now you have all the combinations, right? And then still you need to represent the name for the different combinations, and those names are called as bins, right? The names that you give to a combination of values, or a specific value, or a group of values, or a particular transition is all called as bins, right? So for even the cross, how the automatic bins get generated. And then for the cross, what happens is, because when we combine two variables, not all combinations might be valid, right? So let's say that there is a region for which we are never supposed to do write. Okay, there is a read-only region in the memory for which we are never supposed to do the write. When I just cross two variables together, by default what the simulator will try to do is, what are the possible values a particular variable 1 is going to take, and what are the possible values the variable 2 is going to take. Based on that, it will create the set of expected total values. Now among them, for even the read-only region, the simulator won't know, so it will expect the write access as well, right? Now, but you don't want that. So how do you sort of eliminate those bins, right? For those, you will be using these bins of intersect, matches, these type of operators. You will use it and combine it with the ignore bins. So you should be able to create a subset of the total values by using some expression, and then say that whether that particular bin is a legal bin, or a ignore bin, or a illegal bin, right? So those are some of the functions and the operators that will be present for the crosses bin definition and management. And then we will see we have set of options that control how each of these element behaves, that how does a cover group as a whole behave, how does a cover point behave, how does a cross behave. Now each of these elements are contributing to the overall score, coverage score, right? So through these options we can control how they contribute. So we'll look at them. And then sampling, right? So when does the cover group samples these variables or expressions? So when does it do that? So there are two ways to do it. You can invoke an explicit sample call on a cover group, or you can define a sampling event where on every occurrence of the sampling event, the cover group sample gets automatically or the implicitly invoked. So we will look at both of them. So these are the dimensions that we need to look at. So as we had looked at even at the beginning, we need to understand what is cover point, what is cross, and then how do we manage the bins in each of those cases, and then how do we control the options so that the coverage metric, the way it gets generated, is meaningful for our design. How do you use the options to control that? And then fourth dimension is how do you set up the sampling. So depending on what type of area that you are trying to cover, you have to use the appropriate sampling. So we will understand that. So once you have understood these four dimensions, you have understood or you have mastered the cover group construct. So cover group, just to quickly summarize, it encapsulates the specification of your coverage model, and it contains this component. So whenever we say cover group, you need to, so we have been trying to give you a thought process for every construct, right? So the thought process for cover group, the lines on which you need to think are like when to sample, that's the first point. Whether you want to use an implicit clocking event to synchronize the coverage, or do you want to call an explicit coverage sampling through a sample function. So that's the first thing you want to think. And then second thing is what to sample. So that information, either you can pass it through a formal argument or variables in the scope where cover group is defined, either the properties of the class, typically it will be properties of the class, and then the coverage specification, that depending on the number of variables you want to define the cover points to cover those variables or expressions, and then use those cover points to build the crosses when you need the combinations that needs to be covered. And sometimes you might be using defining a cover point only to create a cross, in which case you don't want like a double reporting of the cover point, right? So those cases, how to use options to eliminate that particular cover point from being reported, because in the cross anyway it will get reported. So that is what is the coverage specification. And then how to use these coverage options such that, like what I talked about, that how do you eliminate that particular cover point that's only meant to be used in the cross, or how do you define that like when I have multiple cover groups that I have defined as a part of my requirements, it's possible that one cover group might be more important than the other. So how do you specify the weights to enhance its importance, right? So those are the things that we will look into more details as we go further. Okay, let's look at one complete cover group solution. So we will slowly start introducing few of the UVM, the base classes as well. We're not going to go into the detail, but just that we start training our eyes so that when we go into the UVM, it becomes slightly simpler. So in UVM, what we do is we kind of implement there is a base class called UVM subscriber that's used for implementing the functional coverage. So we are just implementing one register access, coverage module, or the coverage model, and that coverage model is extending the UVM subscriber, and it's receiving this APB type of a sequence item, so that UART DUT we have has a APB interface through which the UART registers are being accessed. So it will receive a APB sequence item from the monitor. And so the way this UVM subscriber base class works is, whenever the UVM monitor detects a transaction, it calls this function write, which is a built-in function that's already present within the UVM subscriber. It's a virtual function. It will call this write. And within this write implementation, write virtual function implementation, you can define any coverage sampling. So that's the overall broad idea. Don't worry too much about those details yet. Just want to sort of start giving you a flavor of it. So beyond that, let's understand what's important for us. So there is a 6-step process for implementing the functional coverage. Okay, so the first part is that we have to declare the cover group. Okay, so this overall we have this cover group and then end cover group. So we have done the declaration. So we'll go into the sub steps. So let's understand the main parts. So we have declared a cover group, and this cover group, since it's a part of class, it becomes a embedded cover group. Okay, and for the embedded cover group, what happens is, as I had told you, there is already one handle that gets created with the same name as cover group. So our cover group name is reg underscore access underscore CG. So one handle with a reg underscore access underscore CG is automatically created. Okay, so you don't need to again say reg underscore access underscore CG, which is your coverage type name or the cover group type name, and then space reg underscore access underscore CG semicolon. So that line you don't have to write for the embedded cover group. So that handle is already present. So as a second major step, what you do is you say new. Okay, and third step here we are using a explicit sampling method. So in the explicit sampling method, what we do is we call dot sample function that's already built into cover group, like the way we had dot randomize, which was already built into the class, right? So like a dot sample is a already built-in method into the cover group. Okay, so when I call dot sample, what it does is it samples the various cover points and crosses that I have defined from the variables that I have associated. Okay, so now let's look into it. So it's a three major step. I have declaration for my cover group, and then I have constructed my cover group using the new, and third I am calling the sample. So these are the three major steps, but then we have the sub steps. So let's look at those. So first is we create the cover group name, right? And then second, within the cover group name we define these options, so which control the behavior. So we will look into each of these in detail, don't worry about it, just understand the fact that how the overall structure looks like. So we are defining the options for this particular cover group instance over here. Then we are defining the cover points. So cover points, as we had talked about it, that we have to attach one cover point for a variable or an expression that you need to cover. You need to attach a cover point for that. So we are attaching for this properties. So these are the properties of the class. So I have bit write enable and bit 7:0 address. So these are the two properties, and what we are doing is we are accessing those properties based on the scope. Because this cover group is present within this particular class, it has the scope based visibility to look at the properties, and anyway these are public properties. Even if we had a local or a protected qualifier for these properties, still our cover group would have been able to access it. Since they are public properties anyway, it has the visibility. So I am saying, I am giving a name of the cover point colon cover point, this is a keyword, and I am saying WE, which is the property of this particular class which I can access, and then I am defining two bins. So bins are just the sort of name that gets associated with the value. So when the WE is 0, then I am calling the bin as read, and when the WE is 1, I am calling the bin as write. Okay, and then I am creating another cover point, and I am giving the name of the cover point colon cover point keyword, and then again this variable, this property is nothing but this property that I have created within the class, and I am declaring few specific addresses that I am interested. So this is a register, so I am showing, although there are many registers, I am just showing few of them because of the the space constraint. So I am showing when the data register access is done, whenever the address 0 is accessed, it's accessing data register, and when the address hex 4 is being accessed, it's the IER register, and when the address hex 8 is being accessed, it's the IIR underscore FCR register that's being accessed. So I'm giving these names. So what happens is, in the coverage report, I will be able to see if the WE took value of only 1 and it never took a value of 0, then I will be able to see that, okay, the read has never happened. Okay, so whenever I call sample, let's say every time I called sample, it was always the value was 1, then the simulator will report that the bin read was not hit. Okay, and that gives me a very good idea that I need to enable read. Similarly, it will sample the address, and then it will look for these values. If these values are found, then this particular bin is marked as hit, and it also implements a counter per bin. Okay, so for each of these bin, it implements a counter such that whenever this particular value is sampled, it will increment that particular count. Okay, so that's what it's going to do. And then next we define the cross, like we had seen that we are able to see both the read and write, and then we are able to see independently the each of addresses being accessed. Now we want to make sure that like when we put them together as a combination, whether we have done both the read-write access to all of these addresses. We want to see that. So that's where we are saying we are giving the name of the cross, colon, cross is a keyword, and we are listing the cover point names. So here you have to list the cover point names. So we are listing this RW is the name of the cover point, and then this ADDR is the name of the cover point. We are doing it in the comma separated list. So that's how you create a cross. And then here I am defining some of the bins that are not relevant. Okay, so here what I am saying is bins of address, which means that it is going to give me all these bins intersect with 14 and 18. Okay, so of course I have not defined those bins because I have removed them for the sake of saving the space, but there were bins that were defined for the 14 and 18. So I am saying bins of address which will give all those address, which will also include 14 and 18, and bins of read write intersecting with 1, which means that write. Okay, so any writes to these two addresses I don't need to track, right? That's what I'm saying, and rest of them I want to track, so that here in this case what it's going to do is for the data address, whether the read has happened, it is going to keep track of the count, whether write has happened, it's going to keep track of the count. For the IER register, which is at the address 4, it's going to track whether both the read and write have happened, so on and so forth. For every value of address, it's going to check whether both the read and write have taken place. So that's what the cross will do. And of course this is the, so at this point we have defined this cross, and now we come to instancing it. So this name of the handle is already present because it's a embedded cover group, and then I am calling new, which constructs this cover group and enables it for the usage. And since it doesn't have any implicit sampling event defined, we have to call this sample explicitly. So what happens as a part of this overall subscriber, that whenever monitor has detected an access, it's going to invoke this write function, and when it invokes a write function, it's going to give a transaction of the type APB sequence item, and in that transaction again we have these fields WE and address. So those fields I am assigning it to my local properties, because from those local properties is what I am feeding to the cover group, and I am calling that particular cover group dot sample. And whenever I call sample, what it does is it looks into the values of these particular variables and updates all the counters belonging to these cover points and cross. Let's take an example. So let's say I got an APB sequence item, and that sequence item happened to be a write, and it happened to be write to, let's say, address 4. So what all happens is, so it will come in and it will look at, it will look into this cover point WE, and it will look at that, okay, I have two bins, and it will see that it's matching, the value 1 is matching with the write bin. So the count for the write bin, it will increment by 1. Okay, and then it will come to this address cover point, and it will look that, okay, the value of the address is, let's say, 4. Then it will increment the bin corresponding to that particular address IER by 1, right? So the IER's bin count will get incremented, and then it will come to the cross. Okay, and then it sees that the combination is 1, that 8 hex 4 and the write value of 1. So you will have a bin for that particular combination. So it will be a bin created for a combination of a value of write of 1 and the address of 4, right? So those that particular count will get incremented. Okay, and that's what will be the updates that will happen. And subsequently, every time a new transaction comes in, I keep on calling dot sample function, and it will go through the same process and keep incrementing these counts, and all these counts eventually at the end of the simulation get reported into a database. And so for every test, a database gets dumped, and at the end of the regression, for as we had seen in the overall coverage closure flow, we take all those databases, merge them to create a final coverage number, and the final coverage number is a weighted average of all these cover groups. And how do we assign the weight? That we will look at when we go to the coverage options. So each of the cover group is going to have a weight, and whatever is the score that is created by that particular cover group will be taken into consideration to find out the final functional coverage number. We looked at the complete example of the functional coverage in the previous slide, and we also went through like when the transactions arrive, how the coverage gets evaluated. Now let's take one real example wherein we will send a transaction to the cover group that we already saw, and the reg access CG cover group that we already saw, which had 2 cover points and 1 cross, and each of those cover points had like a 2 bins. The read write had 1 read bin and 1 write bin, and then the address, we had figured out 3 addresses which were 0, 4 and 8, and then we had done a cross of the read write and the address cover points, right? So this is what we had created. Now what we will do in this current slide is, let's send one transaction to the sample function of the previous cover group, and we will sample the coverage and then look at how the simulator would report that particular coverage, so that we can see all the coverage computation that we talked about in real action. Okay, so what we are going to do is, let's say that we created this transaction wherein our transaction had the write enable equal to 1, meaning that it's a write, and the address that we are sending the write is hex 4. Okay, so if I sent this with this transaction, I called cg.sample. These were the values that were assigned to those local variables present in the class, and then I called cg.sample, and then I finished the simulation for that particular test, and I then dumped the coverage report. How does it look like? Okay, so this is the way typically the coverage report shows up. This is the screenshot from the simulator. So what we have to notice is the coverage would be reported in 2 ways. Of course, this reporting varies based on the options, but this is the fundamental concept. So when we set different type of options, how the coverage report will look like, we'll look at those towards the end. But for now, we will just look at from the point of view of the coverage computation point of view. Okay, so but for the completeness, to make sense of this report, I am going to tell you briefly that how the overall coverage gets reported. So in the overall coverage, there will be 2 components per cover group. So here we are talking about only single cover group, right? Because we have created only 1 cover group in this particular example. So for every cover group, what gets reported is there are 2 components. Okay, one component wherein the reporting is done as a cover group as a whole. Okay, so what do I mean by that is that, as we know, a cover group is a data type, and I can create multiple instances of this particular cover group. So what this will report at the top, the first one is overall, like I might have 4 or 5 instances, but when I aggregate the information across all the instances as a overall cover group type, what is the result reported, right? So that is what is reported first. And second is you get per instance breakup of that particular information. So now if you had 4 instances, per instance, you know, what is the coverage that we have seen, that will get reported. And in order to get this per instance coverage reported, what we would need is we would need to set this option called option per instance. So there is this option variable that is available. We will talk about it towards the end of this session. So if you set it, then what it will do is, along with giving aggregated coverage across all cover groups, it will also provide the instance level cover group information. So coming back to understanding how the reporting is done, or how the counting aspect that we were talking about happens, let's to see that in action, let's look at this particular instance coverage. Let's go bottom up, and we have created only 1 instance. Okay, so this is our instance, and we have sent this 1 transaction. We have sent only 1 transaction. So what we are expecting is we have these 2 cover points. We have read write cover point and we have address cover point. And if you remember, so we had these 2 bin names that we had given for the values of 0 and 1. So this bin read was a value of 0, bin write was a value of 1, and I see that the write has gotten hit with the 1. Okay, so this is not the value 0 and 1 that we had initialized, but this is rather indicating the count over here. That is how many times a particular bin has been hit. That is what this is indicating. So bin write has been hit once because I have sent this transaction which contained WE equal to 1. Okay, now let's come to the cover point address. In the cover point address, we have three bins. We had the data which was for the value of 0, and we had IER which was address of 8x4, and then the bin IIR FCR which was 8 hex 8, right? So those were the bin values that we had specified. And if you see over here, the bin IER has been hit once because we have sent the address as 8 hex 4. The bin IER, it matches with that particular value, so the bin count for the bin IER has been incremented by 1. Let's look at the cross that we had defined, which was between this cover point read write and the cover point address. So first thing we need to note over here is, as we had discussed, it will create automatically these bins. Okay, so what are the bins that it has created? If you see, it has created read to the data register, write to the data register. Okay, read to the IER register and write to the IER register, and then read to the IIR FCR and write to the IR FCR. That is, we had expected. All the combination of the bin values that are present between the two cover points that we had crossed, all the combinations have been captured. Okay, this combinations gets created automatically. Among these combinations, if you put some ignore bins, those will get ignored. Of course, in our example, those ignore bin addresses we had not defined in the cover point, so those are not taking effect. But if you define valid ignore bins, then some of these bins that get created, they will get ignored. You will not get the the counter assigned to them. So now here what we have done is, we have sent the access with WE equal to 1 and address equal to 8 hex 4. So if you look at it over here, so that is nothing but write to the IER register. So if I see write to the IER register, that particular bin count has been incremented by 1. Okay, so this is how the bin counts will keep incrementing. If I send more transactions, the appropriate counts will increment further. Now let's look at this particular result. So it is saying 16.6% for this particular cross. So what does this mean? So if you look at it over here, so we have these 6 bins, because this 2 and 3, right? The combination of these two is leading to the 6 bins, and among 6 bins only it is one of them has been hit. So it is 1 by 6, which is 16.6%. So similarly, if we look at the cover point address, we have 3 bins, and among them one bin is getting hit. So it is 33%, which is 1 by 3. Okay, irrespective of the number of times this gets hit, it is, once it is hit, it's hit, so it will contribute to like 1, right? So 1 divided by 3, it is becoming 33. So if we similarly look at the read write, the write is hit, read is not hit. So the percentage for this particular cover point is 50%. So the read write cover point is 50% because we are issuing only write. Address is 33% because we are covering 1 out of 3 addresses, and the cross between these two read write cover point and the address, which contains 6 bins, one of them is getting hit, so it is 16.6%. okay, so now if we look at the overall percentage at the reg access CG level, at this particular instance level, so what it does over here is, it averages the percentage of all the components that are present within that particular cover group. So what are the components? I have 2 cover points and I have 1 cross. So whatever the percentage that is reported for each one of them, it averages. For example, what it will do is, it will do 50 plus this 33, will be approximately like 83.3, and then we have 16.6 which will become 99.9, and that 99.9 divided by 3 components, so that is your 33.3. okay, so that is how it averages and finds out the overall number at the instance level. Now if we had multiple instances, then that would have again averaged out at the overall cover group level. okay, so there it would have done that, but there it would do a weighted aggregation, weighted average aggregation. It would do that, and how to set the weight, as we have talked about, we'll look into it towards the end of the session. So it will do a weighted average for the overall cover group type at that particular level among all the instances that we have defined. Weights can be defined either at instance level for each of the cover points, and crosses also we can define weights. So it will take all of them into consideration and create a final value for the type at the type level by aggregating all of the instance level. And in this case, since we do not have multiple instances, whatever our one instance values that we are reporting, the same information is showing up at the overall cover group level as well. So this is how the overall coverage gets calculated and gets reported. Let's take one more example just to build the clarity in terms of counts especially. So in this case, what we are trying to do is we will take 4 transactions. Okay, so what we are doing among those 4 transactions, we have about 3 writes and 1 read. Okay, and then we are issuing 3 accesses to this address 4, and we are issuing 1 access to 8. Okay, so let's quickly look at it from the counts point of view. So if I look at read, I am seeing that it's hit once. Okay, but if I look at write, it's being hit thrice. That's because we have issued the 3 write accesses, right? The transaction 1, transaction 3 and transaction 4, all of them are issuing write, so we are able to see the write count of 3. And since both the bins of this particular cover point are hit, it's showing now the 100%, the 100% as the covered from this cover point of view. If we look at the address cover point, then our IER, which is the address value of 4, it's hit thrice, because we are issuing 3 accesses to address 4, so it's hit thrice. And then the we are issuing 1 access to the address 8x8, and that happens to be our IIR FCR register, and that's hit once. Okay, so you can see how the bin count gets updated. And if we look at from the cross point of view, we see that we have 1 read to IER, which is nothing but our transaction 2. So we are doing 1 read to IER, and that we can see over here. And then we have write and IER is being hit twice. So those are these 2 writes, where transaction 3 and the transaction 1 both are doing the write to address 4, and that we can see the count, the cross bin count getting incremented by 2. And then we have 1 write to IIR FCR, which is nothing but our transaction 4. Okay, so and then appropriately, since you can see that out of 6 we have 3 bins that are hit, and hence it has become 50%. Okay, and now here 2 out of 3 bins are hit, so it has become 66%, right? And here of course everything is hit, so it has become 100%. So you can correlate that the calculations are holding up, and you are able to see the bin count concept that we talked about, that every value is tracked as a counter, that also is holding up with this particular example. Let's look at one more complete cover group example, and let's demonstrate 2 points over here. One, if you want to pass arguments to a particular cover group, how you can do it, and then if you want to define an implicit sampling event, how do you do it? Okay, so we have this cover group CG, and in this parenthesis we are passing these 4 arguments. We are saying ref int of a, and this ref means it is passed by reference. Okay, so if you pass by value, then what happens is only when you create that particular CG, at that point, create meaning when you call the new, whatever the value that is present in that particular variable gets sampled again and again. Okay, so if you are using a particular variable as a part of your cover point, then you have to pass it through the ref. But if you are using a particular input argument to either define an option or to construct some bin, those can be, you can pass them by value. There is not a problem, because those you cannot change anyway. Okay, so these bins that you have to remember, these bins get constructed when you call new. They don't change, they don't keep on dynamically changing. So in that way, once the cover group is constructed, the bins have to be, the total number of bins have to be none, because we need to allocate counters for them, right? So that's a computation, memory, everything needs to be allocated for them. So that has to be non-statically at the point of cover group creation. So at the point of cover group creation, everything that needs to happen with respect to bins has to be defined. It cannot be any further than that. At the point of new, all the bin related information, all the option related information must be resolved. It cannot be changed once you have, like, you cannot, once you have done a new, you can't go and add one more new bin, or you cannot go and change the value of the value contained within the bin, or the name of the bin, or you add new cover points, adding new crosses. Nothing you can do once the cover group is constructed. So at the point of construction itself, all of that information has to be defined. Some of the options can be changed. We will talk about it during the end of the session. But for the good bit of all the information about the cover group, it has to be fixed at the point of the construction. So because of that, those values you can pass by value, because they will be anyway sampled once and they will be constructed. But if you are using a variable that you are passing it as an argument, that you plan to use it in the cover point, those have to be passed by reference only, because every time you sample, it needs to pick up the new value, not the only value that was passed when it was constructed. Okay, so here we are passing, there are two more variables. These two we are passing by value, and then the third one, int c, also we are passing by value. Let's look at quickly a usage of these two. So if we see this low and high, we are using it for constructing the bins. Okay, so now this good bin will be hit whenever the value that is sampled for this particular variable array is in this range. So whenever it is in this low to high range, then the hit count for the bin good will be incremented. Okay, now, and then we have this one bin bad default. What does this mean? We will look at it in the subsequent slides. What basic, like, quick definition of it is, whatever that is not in the whatever that does not cause hit of the bin good will cause hit of the bin bad. Okay, but this default bins, they do not get reported in your coverage. I mean, they do not actually, they get reported, but they don't participate in the coverage calculations. So you generally do this to find out, oh, you were expecting only these values if some other values are showing up. Okay, in order to find that out, you can use the default bin. Now let's come back to and of course this I wanted to complete all the arguments. So we have looked at high and low for constructing the bin, and this last pass by value parameter c we are using to set the weight. Okay, so this is a way option.weight can be set, and this weight gets eventually utilized for calculating the weighted average coverage number in the final report. Okay, so this will be used, and this also is assigned at the point of your cover group construction. And then we are defining an implicit sampling event with the help of a clock. Now we are showing that this is a clock, but it can be any event. Okay, so like as we had seen in the assertions, we typically used to use a clock, but it doesn't have to be clock all the time. It can be any signal, or even the event data type can be used. But you specify an event when this particular cover group needs to be sampled, and in this case we are using at passage of the clock. Now what happens is, on every passage of the clock, automatically this particular cover group dot sample function that we had seen in the previous example, it gets called implicitly and automatically. Okay, and for the pass by reference, it will automatically take the values and it will be able to sample them. And this passing the arguments has the advantage that now you can customize each of the cover group. So this way you can build more reusable cover groups. If I had hard coded this range over here, then the utility of this cover group is low, because that's hard coded. Now as I'm able to pass, the C1 is going to look for the range of values between 0 to 50, and C2 is going to look for the range of values between 120 to 600, right? So this way I can now customize, I can build much more reusable cover groups using the arguments. and of course the implicit sampling itself is not contributing to any reusability. I'm just combined these two concepts over here, but by passing arguments you can build reusable cover groups, and as you can see we are passing different values and they are going to be behaving differently. Whereas implicit sampling, it shows one more way. So we had seen explicit sampling in the previous example, and here we are seeing the implicit sampling, so that completeness comes up as to you can pick and choose the option. Typically when you are doing the black box coverage for the transactions, you tend to use the explicit sampling, that cg.sample method that we saw, and if you are using it for like a white box type of a coverage, white box meaning something related to microarchitecture, something related to interface where it's already driven by some timing events, then you can use the implicit sampling event for the implementation of those cover groups. Okay, so when you use the event or the implicit sampling, you have one more feature that's available. You can actually use a condition. So here what this means is I'm saying at passage of clock, and notice that it's not if, it's one extra if IFF. I am saying TLP RX valid. Okay, so what happens is that this particular CG TLP will be sampled on a passage of clock if TLP RX valid is asserted. So typically when you look at any signal level interfaces, what happens is like even if you look at simple APB bus or any buses, there is a valid signal that tells when the bus contents are legal, or when that particular value can be consumed, right? So that is a typical use case. So when you are implementing those type of coverages, you can use this IFF to qualify that particular edge where it needs to sample. And not only that, as we talked about, not only that you can use any event, but you can also use a clocking block over here. A clocking block sampling event can also be used, and if you use that, and then if it had a $1 step, which is your default sampling for the clocking block, then the information in the variables would be sampled from the preponed region. Okay, so it will do that. And if it had the skew of 0, which is the normal, like skew of 0 for the clocking block, or in general, it will be sampled in the observed region. Okay, so that's what will happen with respect to cover group. And if you do not specify any implicit sampling, then you have to call the built-in built-in method sample explicitly, as we had seen in the one of the examples. And there in the previous example we had seen embedded cover group, which we had put it in the class, right? And there actually, if you remember, the handle got automatically declared, so we just did new, and it was using the variables that were present in the scope of the class. But here we have put this cover group in a module. Okay, so when you put it in the module or in the interface, then also whatever the local variables that are available within the scope, for example the ports over here, are accessible to the cover group. Okay, so I am able to sample these ports, and if there are any internal reg or wire available within this module, those also are visible to this cover group as a part of its scoping rules. And I will have to explicitly create a handle as well. There's no implicit handle available. So here I am doing it in one line, but I still have to declare the handle and then call new. Whereas in the previous example, I just have to use the implicit handle and call new. Even in class, you can again declare additional handles. If let's say you wanted an array of cover groups for implementing multiple ports, that would not be available. So you still have to declare multiple handles and new them, but one implicit handle will be available when you do the embedded cover group. So that's one extra feature that you gain when you implement it within the class. But when you implement it within the module or the interfaces or the program blocks or the checker blocks, then you have to explicitly create the handle and then construct it. Okay, so this gives sort of broadly what the cover group construct as a whole is capable of doing and how it gets reported.